All right, let's dive right into this explainer. Today, we're breaking down the actual physics and engineering behind a real modern marvel, capturing gigawatts of solar energy in space and beaming it directly down to Earth. Now, you might be wondering, how exactly do we pull that off? Because the ultimate bottleneck of space solar power isn't the solar panels themselves. It's safely transmitting all that massive energy through the vacuum of space and then through Earth's atmosphere without a single wire. We've got a great roadmap today. We'll start with the vision, look at microwaves versus lasers, run the atmospheric gauntlet, and then cover ground capture, safety, and our final engineering verdict.
So let's start with part one, the space solar vision. Picture this, massive solar satellite sitting way up in geostationary orbit, capturing bright, continuous sunlight. Unlike the panels you see on rooftops, these orbital arrays harvest intense energy 24/7. They are completely free from weather delays or, nighttime.
And this brilliantly illustrates the whole setup. The end-to-end architecture is basically a three-step chain. First, photovoltaic arrays generate the power. Then, orbital transmitters condition it to direct current. Finally, they beam it straight down to a grid-tied ground station.
Moving into our second section, let's talk about the transmission itself, microwaves versus lasers. This technological face-off really comes down to two distinct architectures. On one hand, you have a laser diode paired with a photovoltaic array. On the other, you've got a microwave antenna beaming power to a specialized receiving rectenna on the ground. It's essentially a battle of wavelengths. We're comparing long 2.45 gigahertz microwave radio waves against microscopic near-infrared lasers. And honestly, this single physical difference literally dictates everything about how the system works.
The absolutely critical factor here is beam divergence, specifically what's called the Gaubo-Brown effect. As an electromagnetic beam travels 36,000 kilometers from space, it naturally spreads out. Because of the diffraction limit, longer microwaves actually require a massive kilometer-wide orbital transmitter just to stay focused, while lasers allow for a highly compact array.
Okay, section 3, the atmospheric gauntlet. Now, what's really interesting about this is how we treat Earth's atmosphere like a giant obstacle course. Plunging toward Earth, the energy beam first has to slice cleanly right through the upper atmosphere's plasma layer, the ionosphere, without scattering or reflecting off target. As the wave hits the lower troposphere, vibrating molecules and weather become the ultimate obstacles. Lasers try to target precise atmospheric windows, but the second heavy rain and storm clouds roll in, they suffer severe scattering. The beam basically breaks apart against the water droplets. Microwaves, on the other hand, they punch smoothly through heavy rain like it's absolutely nothing. Which brings us to section 4, ground capture and conversion. For microwaves, the capture process happens at a rectenna. Zooming in, as the spread-out, oscillating, alternating current wave hits a dipole element, it passes through a Schottky diode. This instantly flattens the wave into steady, usable direct current electricity. But this translates to vastly different ground footprints. A microwave rectenna requires a massive open mesh ground field to catch that diverging power density safely. A laser receiver, though, only needs compact germanium panels. That makes lasers ideal for small, remote, off-grid locations. All right, on to section 5, safety and power grids. So, the crucial point here, especially to dispel those Hollywood death ray fears, is that models show the peak incident power density on the ground is only about 3.35 to 5.72 watts per square meter. That energy is incredibly diffuse. It's actually way less intense than the midday sun on your skin. To put that into perspective, as we can see in the data, this power density safely falls well below the strict international safety limits for the general public, which is capped at 10 watts per square meter. So it's completely safe. Let's move to section 6 and our final engineering verdict. So, the takeaway? Ultimately, microwaves look like the most feasible victor for large-scale terrestrial grid integration, mainly because of their unparalleled all-weather reliability. A modern city needs steady power. Lasers, however, carve out a really crucial niche for powering compact, off-grid deployments like drones or remote sensors. As the research points out, space-based solar power is a transformative vision for global energy sustainability by 2050, aiming to provide continuous 24/7 clean energy. The technical feasibility we just walked through points directly toward a future of total global energy independence. So, what do you think? Which technology will ultimately win this space solar race to power our future? The vast all-weather microwave grid or the precise pinpoint laser? Let that sink in because the race has officially begun.